Welcome back. Let's go ahead and finish Module 4, this Financial Mathematics unit. Here's an example of a more realistic kind of problem than what we've been considering so far. It says, suppose you deposit $50 per month at the end of each month in a bank account paying 15% annual interest compounded monthly. How much will be in the account after 3 months, after 18 months, after any other amount of time? Notice that this is a more realistic type of situation, investment situation, than we've been considering so far. For most of us, when we're saving up for retirement or for our kids' college education, to buy a house at some point in the future, we don't put down a lump sum and walk away and wait 30 years and then come back and pick up the amount that it's grown to. That's just not the way people do investing. What we do is, because we get paid weekly or monthly, each pay period we probably have a little bit of our paycheck deposited into some type of savings account, and that happens month by month by month or week by week by week, and it grows over time. That's the way people invest, a little bit at a time, and that's called an installment investment. The installments referring to the individual small investment amounts made per period, or it's also called a sinking fund. This is a more realistic situation. Notice it's a more complicated situation as well. In the previous type of investments, there was one principal put down, and then we could apply a formula to find out how much it would grow to at the end of the investment period. But now there are many principals put down. There's a $50 put down at the end of the first month, the $50 put down at the end of the second month, the $50 put down at the end of the third month, and so on. And all of those $50 investments grow over a slightly different period of time, and so we're going to have to consider each investment separately to some extent. So more realistic, but more complicated. Well, let's take a look at two ways to do this problem. One is using Microsoft Excel, a spreadsheet, and the other is developing a new type of formula and then just using standard mathematics. All right, let's look at the spreadsheet way, and as a warm-up to that, let's do a couple of calculations by hand. In this scenario, after 1 month, I will have $50 in the account. I just deposited it. After 2 months, well, this first $50 that I deposited is going to grow. So $50, I'm just copying this down, but then it's going to earn interest. The $50 is going to earn interest at 15% annually divided by 12 months per year to get the monthly interest rate. I'll put that in brackets. That's how much the first $50 grows to, but then at the end of the second month I also deposit another $50. And a calculator will show that this is 100.63. The $100 I deposited over the 2 pay periods, the 63 cents is the interest. After 3 months, what do we have? Well, the $100.63 from the second month comes forward, and it earns interest at 0.15 divided by 12, the monthly interest rate, and then I tack on another $50. I could work this out. Notice that there's perhaps a slightly simpler way to write this. The first 2 terms have the $100.63, so I could factor that out and compute it this way, and works out to be $151.88. Alright, I could continue to do the problem manually this way and go up to this is 3 months. I could go up to 18 months if I wanted. This is becoming tedious to do if I wanted to go to 18 months, and especially if I wanted to go to, say, 30 years. So go ahead and pause the video and bring up Microsoft Excel if you don't already have it launched. Microsoft Excel. At the bottom of the page is the type of spreadsheet that we want to end up with. In fact, a little more than what I will demonstrate here for purposes of teaching. And on the next page at the top are some directions that I will describe verbally. So let's go to Excel. And if you'll notice on the Outcomes page, I want to have a column containing the number of the months that I'm talking about. So in cell A1, I'll put a header month. And then I would like to number from 1 to 18 down this column. I could type all of the numbers. Let me show you something a slightly different way. Enter the 1, go back onto that cell, and then notice that there is a dark square box on the lower right hand corner. If I move the cursor onto that square box, it's ready to copy that cell. And the way you copy is hold down the left mouse button. Click and hold down the left mouse button and then drag down through row 19. Release the mouse button and oh, that doesn't look like what I wanted. I really wanted 1, 2, 3, 4, 5 and so on. But before I do anything else, if I come and hover on this little dialog box that's on the lower right hand corner of the area to which I copied, left click on this drop down arrow and there's an option Fill Series. If I choose this, click on that, then it does exactly what I said. You have to do that after you've copied, before you do anything else in the worksheet. Alright, in the next column I want to include totals in the account at the ends of the corresponding months. And so I'm starting out with $50, and now I want to enter amounts corresponding to the entries on the page that I just showed manually. Let's enter this with an Excel formula. When you want to enter a formula into a cell, type the equals key. That triggers Excel to now expect a mathematical formula. And what I would like is, remember, this expression. The first time, if I had factored out the 50 as I could have out of this term in brackets, I'd have 50 times 1 plus 0.015 over 12. And then the second time around, I have 100.63 times 1 plus 1.15 over 12, and so on. So in Excel, what I really want to say is whatever the previous amount was, put it outside the parentheses, and then multiply by this 1 plus 0.15 divided by 12. Okay, in Excel, the previous amount in each month is going to be contained in the cell right above it. And so if I come up here and click on the cell above, that's referencing the $50, but more importantly, it's referencing the previous month's amount. Now, that gets multiplied by, so times quantity, 1 plus 0.15 divided by 12. And then let's add the $50 deposit for the second month. So here's what the formula looks like. As soon as I push enter, it gets evaluated. And then in cell B4, to calculate the amount after the third month, I really want to do exactly the same thing as I did in the formula for cell B3, to calculate the amount after the second month, except I don't want $50 right here out front. I want the 100.625, but that's the point. I want the previous cell times this expression in parentheses. And the way to make Excel do that is to drag or copy this formula down through these cells. Again, let me go to the lower right hand corner, left click, hold, and drag down, and release. Now let's come back here and look at these formulas and see what happened. here's the 50 that I entered, here's the formula that we just entered a minute ago, and when I go to the next line, here is a formula that I copied, but notice something changed. Instead of there being a B2 here, now there's a B3, and that's exactly what I want, because B3 contains the amount from the previous month. And when I go down one more, now in cell B5 it's referencing cell B4, in cell B6 it's referencing cell B5, and so on. So this is exactly what I want Excel to do. And now I can just read off the amounts. So here is the $151.88 after the third month, and to answer the other question, after 18 months there would be $1,002.31. Okay, that showed how to do the calculation using Excel. You can use, you can add a graph if you want, and I'll ask you to do this in a later project to go ahead and graph the amount and see it growing visually as well. Let's now go to answering a question like this. If you deposit $20 per month, how much will you have in the account after 18 months? If you deposit $100 per month, how much will you have in the account after 10 years? And how much would you have to deposit each month to have $1,000 in the account in 10 years? Let's go back to Excel. Excel again, and a clean worksheet. If you have the other one still there, go ahead and delete it or clear it and go to a clean worksheet, and let's go month here and amount again. Let's fill the first column with month amounts. Notice that I'm going to have to go up to 10 years. That's actually 120 months. So here's where it becomes very beneficial to be able to drag down to row 121 and fill that series. So notice now we have 120 months entered. Notice in this problem I'm going to want to change the deposit amount several times, and so let me show you a way to make that more easily done. Let's come over here and put another header called deposit, and right in here I'm going to put, for the first part of the question, $20 for my first deposit amount. But in order to make that easily accessed, let's come and name this cell. I'm going to click on cell D2, and then I'm going to move to this area, the name box, and if I click on that and clear out what's there and type D for deposit and push enter, I have now named this cell cell D. So anytime I want to refer to cell D2, I can just refer to it by name D. Okay, so now what do I want to do? The first month I deposit D. So I can click on cell D2 or type the letter D. And now, next I want to do what? A formula. And it is the previous amount times, I'm doing part 1 plus 0.04, that's 4% annual interest, divided by 12 to convert to monthly interest, and now plus the deposit amount. Here's the formula again, refers to the previous month's amount times our usual expression that computes the amount that grows to, and then plus the deposit for that current month. Alright, for part 1 I want to know how much I have in the account after 18 months, so I'll then drag this formula down to month 18. Okay. And so amount there of $370.38. The answer to part 1. And for part 2, I want to actually go for 10 years. So let's come back here and just continue to drag this formula down over the many, many months down to 10 years is 120 months. Okay, that actually would be the amount if I had deposited $20 per month, like in part 1. But now I'm doing part 2, and the deposit amount was actually $100 per month. So I can simply come and change this one cell and push enter, and there we are. So after 120 months, I come down, and the answer to part 2 is $14,724.98. Okay, and the third part then says, okay, I just want to end up with $1,000 after 10 years. It's not so much. I want to know how much I would have to deposit each month. So obviously that amount would be much less than $100. With $100, it's growing to almost 15,000. I only need to grow to 1,000, so much less. But how much? Let me show you, and then I would like to just come back here and change this amount in cell D2 repeatedly and see what happens to the final amount after the 120 months. Notice that there would be a lot of scrolling involved. I change it, then I'd want to scroll down, then come back and change it, and I want to scroll down. Let me hide some rows. So if I click on row 3, hold, and drag down through all of the rows except the last one, release, and then right click and click hide. Now all of those rows are still there, they're just not displayed. Now I can come here and freely start to change. So $100 was far too much. Well, how about $20 per month? That would grow to $29.44. That's more than I need. So how about $5? That would grow to $736. That's not enough. So how about $8? That would grow to too much. $7, a little too much. $6.50, not quite enough. $6.70, not quite enough. $6.80. Okay, just a little over. $6.79, not quite enough. So it looks like $6.80 would be an appropriate deposit amount to grow to $1,000 over 10 years under these interest rates. Okay, so we just did this example on the page, and now let's switch gears and talk about the other method. This was how to do such problems with Excel. There's another way to do the same type of question, and that's with a mathematical formula. And then after this, you choose whichever method is easier for a given situation. Excel, after you get it set up, is very easy. It's also very error-prone, because if you type just one thing wrong, you get the wrong answer, and you may not know that you're doing something wrong. Let me take just a little mathematical detour to show where the formula comes from. We are going to be doing this problem again, depositing $50 per month at the end of each month in a bank account. Let's assume that we're getting 15% annual interest rate compounded monthly. How much would be in the account after 3 months? Most people would like to get 15% annual interest right now. It's just not available now. Let's go back to a formula for compound interest that went P times 1 plus I to the n. Here, A was the amount at the end, P was the principal deposited, I was the per compounding period interest rate, and N was the number of compounding periods. In this problem, I is R over M is 15%, and interest is compounded 12 times per year, so it's 0.0125. Now, let's approach this problem a little differently than we did before. Before, we worked month by month by month and added up as we went and said, okay, at the end of the third month now, that grows to how much at the end of the fourth month, and then that grows to how much at the end of the fifth month. Let's consider another point of view that says, let's think of these deposit amounts completely independently. So, at the end of the first month, I deposit $50. And I want to grow this over 3 months. So how many compounding periods does this deposit have to grow? 2. I'm at the end of the first month. It gets to grow then over the second and the third months. That's 2 periods. The $50 deposit at the end of the second month only gets to grow for 1 compounding period, 1 month, the third month specifically. And the last $50 doesn't get to grow or compound at all. I deposit it at the end of the third month and then immediately check how much is in the account. Now, how much does this, let's go back and fill in this last column, how much does this amount grow to? The $50 has this 0.0125 monthly interest rate, and it grows over 2 compounding periods. N is the number of compounding periods. So this will grow to 50 times 1 plus 0.0125 squared. And this will grow to 50 times 1 plus 0.0125 to the first, and this will grow to 50 times this expression in parentheses to the 0th power, but anything to the 0th power is 1, and so we won't write it, we'll just write the $50. Alright, so this grows, if you work it out, to $51.26, this to $50.63, and this to $50, and so the total is the sum of these three. Which works out to be 151.89. Now, that's another way to think of the problem, that the individual deposits are then pushed forward to the end, each individually, and then I simply add up the accumulated amounts from each of the individual deposits. It turns out that this summation has a special form, and that's going to be very convenient to take advantage of. I would not like to do this type of calculation over a period of 30 years either. So let's look at a tricky way of adding sums of this form. Suppose, for a simpler example, I want to add 1 plus 3 plus 9 and so on up to 2,187. The special thing about this is it's what's called a geometric series. Each term is 3 times the previous term. Each term is 3 times the previous term. I want to know what that adds to. Let's do something sneaky. If both sides of this equation are equal, then when I multiply by 3, both sides of the new equation are equal, and I'm going to write this new equation up above the old one. So when I multiply s by 3, I get 3s. When I multiply this sequence of terms by 3, each of the terms will get multiplied by 3, so 1 gets multiplied by 3 to become 3. I'm going to write it slid over a little bit. And then this 3 gets multiplied by 3 and becomes 9. This 9 gets multiplied by 3 and becomes 27, and so on. So plus 81, 243, 729, 2187. And finally, this 2187 gets multiplied by 3 to become 6561. Why did I do that? Well, let me draw a line here. I have two equations, one above the other. Let me subtract the second equation from the first, the one we just wrote. Right, if these two things are equal and these two things are equal, then I can take the 3s minus the s and get 2s, and I can take the expression on the right-hand side on top, subtract off the expression on the right-hand side on the bottom. When I do that, notice that something very special happens though. First of all, the 3 minus 3, 9 minus 9, 27 minus 27, 81 minus 81, and so on, all of these terms occur in pairs that cancel. And so all I have left is the 1 on bottom, and since it's being subtracted, it's like there's a 0 here. 0 minus 1 is negative 1. And then out here, there's a 65, 61 that doesn't have a term to cancel it out. And now what was I trying to do? Find s. So here's an equation. Solve for s by dividing both sides by 2. While I'm at it, 6561 plus a negative 1 is 6560. And divided by 2 is 3280. Okay, I could have gotten that probably easier just by adding these terms, but what I'm trying to do is find a technique that works when this summation would have went on a lot longer. Suppose instead of 1, 2, 3, 4, 5, 6, 7, 8 terms, suppose there had been 800 terms of this form. Rather than doing the addition term by term by term, this formula would have fairly quickly let me come up with the value of the sum. And let's do a more general example. We're on our way to developing an actual formula here. So s equals d plus d times x plus d times x squared. This is a geometric series as well. Each term is x times the previous term. So d times x is dx. D times x times another x is dx squared. I take that and multiply by x and I get dx cubed and so on. I'm going to multiply this equation on both sides by something that will force a number of terms to drop out, like in the previous example. In the previous example, we multiplied both sides by 3 because 3 was the ratio here. Each term was 3 times the previous one. Here the ratio is x. Each term is x times the previous one. So multiply both sides by x and get xs on the left, and get d times x is dx. Dx plus times x is dx squared, and so on. Plus dot 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 stands for a bunch of terms in the middle that I'm not writing. Then there will be a dx to the n minus 1, and finally dx to the n minus 1 gets multiplied by x. So remember the rules of exponents. Dx to the n minus 1 times x. That's x to the 1. And when you multiply expressions with common bases like this, the exponents add. So dx to the n minus 1 plus 1 is just dx to the n. And now let's subtract the bottom equation from the top again, and I get x times s minus s on the left, and on the right most of the terms cancel. The only ones that don't are the d, and it's minus d because it's on the bottom, and dx to the n, and it's positive because it's on the top. I'm trying to solve for s in this expression. Let's factor an s out of the left-hand side. So both terms on the left have an s, and if I pull it out, say on the right-hand side, that leaves an x minus 1. On the right-hand side, both terms have a d. Let's pull that out, and I get a minus 1 plus x to the n. And finally, let's solve for s by dividing both sides by x minus 1, and I get d times, I'm going to change the order of the terms. and write this as x to the n minus 1. It's the same thing, and divided by x minus 1. So the algebra may look a little complicated, but it's actually not bad, and it's actually very clever. If I want to know now what this expression is when d is 17 and x is 35 and n is 1013, rather than adding up all those huge number of terms, I can just come down here and plug in those values of d, x, and n and quickly crank out a number. Finally, let's push that formula to the exact situation at hand. A bank account pays interest at a rate R% annually, compounded M times per year. A deposit is made of amount D is made at the end of each compounding period. I do that for T years, and I want a formula for the final amount A. Remember the expression from before that R divided by, oops, there's a typo, this is an M, should be called I, and N equals M times T. So here's the per period interest rate, and here is the number of compounding periods. All right, let's go back and number the compounding periods. 1, 2, 3. Then I'm going to skip a bunch, and I'm ending up with n periods, so the one before that must have been n minus 1, and the one before that must have been n minus 2, and the ones in between were 4, 5, 6, and so on. Each compounding period, I'm depositing the same amount D. And now, how many periods do these have to grow? Well, there are n periods total, and I deposit D at the end of the first period, so it doesn't get to compound over the first period, but it does over all of the remaining periods. If there are n total, and one of them doesn't get it isn't compounded over one of them, it's compounded over the remaining n minus 1. How about the next one? One fewer periods, because it was deposited one period later, so n minus 2 and n minus 3 and so on. Notice the example, numerical example that we did. N was 3, and so we started out with 2, 1, 0. They keep going down by 1 each time, and so here I'm starting out, n is n, and I'm starting out with n minus 1, and they keep going down, n minus 2, n minus 3, and so on. Where do we end up? This one doesn't get to grow at all. The one before it grew for one period, the one before that grew for 2 periods, and then the ones in between for the amounts from 2 to n minus 3. How much does this amount grow to? It's the formula for compound interest was D times 1 plus the per period interest rate, that's I, to the number of periods that this amount was compounded to. Well, that was n minus 1. And the next one, same expression, except it grew to for n minus 2 periods, and the next one for n minus 3 periods, and so on. And so by the time we get near the end, it's compounded for 2 periods, 1 period, and no periods at all. All right, let's add these amounts together to get the total. So I'm going to start adding from the bottom. D plus D times 1 plus I plus D times 1 plus I squared plus a bunch of terms in the middle that I'm not writing, and then plus D times 1 plus I to the n minus 3, D times 1 plus I to the n minus 2, and D times 1 plus I to the n minus 1. Okay, that looks horrible, horrible, I imagine, to you. It even does to me. But it's actually a geometric series. Each term is the previous one multiplied by the quantity 1 plus I. So use previous formula with what we called x to now be the expression 1 plus I. By the previous formula, I mean this formula. And so the amount grows to d times x to the n now becomes 1 plus I to the n minus 1 divided by x minus 1. So x is 1 plus I, and then minus 1. And the numerator is what it is. The denominator simplifies a little bit. We copy the numerator, and the denominator, the 1's cancel, and I just get I. And here is a formula that for sinking funds that appears in the text. Okay, some of you may be feeling a little overwhelmed right at this point with all of this algebra. I will give you this formula on the test, or actually I don't even need to since the tests are open book. But I think it's very enlightening to see where these types of things come from. This is not just something that was pulled out of the air. It's very straightforward, although a little cumbersome mathematics. You just talk about what happens when you add the terms of a geometric series. And in the example that we did, the terms of the individual amounts that deposits grow to do exactly have the form of a geometric series. So let's show some examples then of what you actually need to be able to do. Problems like this. Suppose you're going to put aside a fixed amount of money each month into an account paying 4% annual interest compounded monthly. If you deposit $100 each month for the next 40 years, how much would you end up with? All right, question number 1. Let's work out what the variables in the formula are. I is 4% divided by monthly is 12 times per year. N, the number of deposit periods, is 40 years times, each compounding period is 1 month long, so times 12. D, the deposit amount, is 100. I want to find A. So I go to the formula that we just developed and plug these quantities directly in. And the expression then looks like this. 100 times 1 plus 0.04 divided by 12 to the 40 times 12th power minus 1 divided by 0.04 divided by 12. Alright, let me say just a bit about entering this into your calculator. It's obviously a calculator problem. You can enter these various parts individually and write things down as you go, and I don't entirely object if you do that. So for example, I could type 1 plus 0.04 divided by 12, write that down. I could take 40 times 12, write that down, and so on. One problem with that is every time you write something down, you're probably not going to copy all of the digits in your calculator, and so you're rounding each time. And so as you do these successive calculations, you're rounding, and then you're rounding the rounded result, and then you're rounding the rounded result. And each time you round, you lose a little bit of accuracy, and by the time you get several stages of that going, you can actually round and your answer so much that your answer becomes a little inaccurate. So it's actually better to avoid writing very much down, and better to put quite a bit into the calculator to avoid rounding at all. On the other hand, when the calculator formulas get pretty cumbersome, then it's easy to make mistakes. And so you're going to have to take a happy medium, I think, with the extent to which you're comfortable entering big formulas into the calculator versus writing things down and doing individual rounding and so on. Let me bring up a calculator and show how this could be entered as one large formula without any rounding at all. So here's a simulator of a TI-89 calculator. Some of you may have a graphing calculator such as a TI-83 or TI-84 or perhaps a TI-89. On each of the graphing calculators, the keystrokes are going to look something like this. If you just have a scientific calculator or a calculator on your phone, it'll probably work a little differently, and I could help you out individually, but I can't demonstrate all possible models. All of the TI graphing calculators, would look something fairly similar to this. So I want to enter the expression we just wrote down, 100 times, and now these big square brackets will make one set of parentheses on the calculator, and then there will be another for the 1 plus 0.04 divided by 12. And now on a graphing calculator, the power key is this caret, and to the 40 times 12, so that the 40 times 12 gets multiplied before the power is taken, I need parentheses around that as well. And that's then the entire numerator. So now one more close parenthesis or right parenthesis to be the right big bracket that we drew in our formula, divided by, and now I enter the denominator, and again, in order to get the 0.04 divided by 12 done first, before I divide, I want a set of formulas, a set of parentheses down here as well, 0.04 divided by 12, close parentheses. Again, if I forget this last set of parentheses, what it's going to actually do is divide by this 0.04 and then take that result and divide by 12. But that's not what the mathematics says to do. Division is not commutative. You can't do it in any old order, and it needs to be done in this order. Okay, so if I push enter, the answer to the question looks like it's 148,196. And the TI-89 calculator actually shows you a nice display screen so that you can see whether you've entered things correctly. And this should directly mirror what we wrote down just a little bit ago. The 100 times 1 plus 0.04. Oh, I forgot something important. I forgot the -1. Let me show you how you can edit on a graphing calculator. So the answer is not correct yet. Hang on just a second. Let me come here. And I should have right here entered a -1. This is the beauty of a graphing calculator. You should just come up and change what you want. Let me push enter again. I'm glad I made that mistake actually. I didn't intend to, but I'm glad I did because it shows how you can change things on a graphing calculator. I wanted this -1 because it is indeed part of the formula. So the right answer is $118,000, $118,196. And I come back here, and it is $118,196. If you carry it out to a little more precision, there's actually 13 cents in there, but with a number this large, I wouldn't care too much about the 13 cents. Okay, and the second type of computation, second question says, how much would you have to deposit each month to have $1,000 in 10 years? We actually did this problem before. We did it trial and error on Excel. Let's show how you could do this with a formula. The amount that I want to end up with, the A this time, is $1,000, and the D is what I'm trying to find, the monthly deposit amount. So let's enter the rest of the things into the formula. The time now, the number of years is 10. So it looks like this. And I want to find D. I'll go ahead and algebraically solve for it before I put things in the calculator. You can do that if you want or not, as you wish. What I'm going to do now is take the $1,000 and first multiply both sides by this denominator. So in other words, that comes up here, and then I will take both sides and divide by this expression in brackets, and so it's going to be bringing it down to the denominator. So D equals 1,000 times the 0.04 divided by 12 and divided by the expression in the square brackets that I circled in green. Like this. And if you work that out now, again, plug into a calculator, and it works out to be somewhere between $6.79, $6.80, depending on how you round in this case. Essentially the same thing as we got using Excel. Alright, that finishes Module 4. And to summarize, in sections 1 and 2 of Chapter 21, we talked about the situation where you put down a single deposit and allowed it to accumulate over time, and then ask what is the amount at the end, either using simple or compound interest. In section 4, now that we just did, we dealt with a situation where you're setting aside an identical deposit amount each compounding period, say each month, and asking how much it grows to at the end. This is called a sinking fund or an installment investment. Thanks.